Okay, so let's start. We discussed the antenna radiation pattern, the relation between the illumination function and antenna radiation pattern for the 1D and 2D cases. Now we want to also understand the antenna arrays, how the antenna pattern radiation looks like for an antenna array of antennas. Okay? Because commonly the antennas used in imaging are in the antenna array form. Okay, so it doesn't consist of a single antenna, but it has a small antenna that is repeated, whose illumination function is repeated in the other antenna elements. Okay, so there is an antenna array that consists of antenna elements, and each generally have the same illumination function, S or XY. Okay, so we want to understand antenna radiation pattern again in the far field for antenna arrays. We're going to consider the periodic arrays first. This is, I believe, one of the most commonly used antenna array structure. In the periodic array, we have small antenna elements, okay? And these are periodically repeated. So each has an identical illumination function, which is periodically repeated, okay? So let's say the illumination function for a single antenna element is S or XY this time. And we have an N by M rectangular array of equispaced, equal interval antenna elements. Suppose the distance along X direction is D1, and the distance along Y direction is D2. Okay, we wanna now understand the radiation pattern in terms of each little S or XY. Okay, so what will be my pattern in terms of the illumination function of a single antenna element? Okay, so that's the relationship we want to find. Let's start with that. First, we need to write the illumination function for the overall aperture. Okay, so what is my general aperture function, or the illumination function? We call that SXY. In terms of S0, we have repeated S0s. Okay, so we can write this in this form. Okay, this form should look familiar to you from the first weeks in this course. Okay, so basically we're taking this S0 function, we are shifting it by K times D1 and L times D2 in X and Y direction, as K goes from 0 to M minus 1 and L goes from 0 to M minus 1. But if we just do this shifting, then our antenna aperture will appear here, okay? Actually, including the origin, it's going to appear here. But we want to generally have an antenna array or an array model or periodic structure that is centered at the origin. So we need to basically shift this portion to the origin. Okay, that requires shifting it by half of its length, which is N minus 1 D1 divided by 2 and M minus 1 D2 divided by 2. Okay, if we do that, then we are going to get this support. Okay, so that's going to be our S0, the relationship of S0 with the overall illumination function. Okay, now we want to find the pattern for this illumination function. So we need to take the Fourier transform of this and evaluate at the angles that we want, okay, or evaluate at the frequencies that we want. To take the Fourier transform, it's a good idea to express this in terms of some functions that we defined before, like the conv function. Remember that we can write the periodically repeated structures like this, or the signals like this, as a convolution of each signal S0 with a conv function. Remember that two-dimensional conv function is periodic impulse train, but it is finite. Okay, there are finitely many periodic impulses. Okay, with distance d1 and distance d2 along x and y direction. So this is the two-dimensional conv function of n by m scaled by d1 and d2. N and m here tells us the number of impulses we have in each direction, and d1 and d2 tells us the distance between impulses along each direction. Okay, if we convolve this S0xy with this finite impulse string, we're going to get this structure. And then we can take the Fourier transform. For Fourier transform, we will now have a nice expression once we express it in terms of convs. The 2D Fourier transform of this is the Fourier transform of S0. Convolution becomes multiplication, and multiplication with the Fourier transform of this. The Fourier transform of two-dimensional conv was, remember, that it was a two-dimensional Dirichlet function. But both the conv function and Dirichlet function are separable functions. So you can write them as multiplication of two one-dimensional Dirichlet functions or two one-dimensional conv functions. Okay, you need to also take into account the scaling effect. So you're going to have d1, d2 multiplication here and d1, d2 multiplications here. And that's going to be your 2D Fourier transform. And the antenna pattern is just expressed in terms of this Fourier transform. What was it? Let's remember. The 2D antenna pattern was 1 over lambda square. This S evaluated at these frequencies. If you do that, you need to evaluate S0 at this frequencies. Okay, let's call that E0 phi psi. And then this term evaluated also at these frequencies. Okay, we're going to replace fx and fy with these values. So we're going to get this Dirichlet evaluated at these points with d1, d2 factor in front. Okay, so that's going to be our expression. Okay, here we replace this S0 term, the Fourier transform S0 term, with the antenna radiation pattern of a single element, which we call E0. Okay, so now we have the overall antenna pattern expressed in terms of antenna pattern of a single element. Okay, what is it? It's the Dirichlet modulated. So the single elements or single antennas pattern is modulated with the Dirichlet function, and that gives us the overall pattern for the array, antenna array. Okay, so how will this look like? Let's visualize that. As an example, for S0, let's consider a uniformly illuminated square antenna aperture, antenna element. Okay, so my single element in this array will have rectangular illumination, uniform illumination, with a size of length L. Okay, so this is also the example we skipped before here, 2D case example, fully illuminated square aperture. Let's first find how the radiation pattern will look like for the single element. Okay, this 2D uniform illumination function. It's going to be the Fourier transform of this. So the sinc L fx, instead of fx, we're expressing this thing, writing this term. Okay, so we have this, and same here, and we have this scaling. Okay, so this is my antenna aperture. This is my radiation pattern for a single antenna element. Okay, so it's going to be this two-dimensional sinc function. But again, we view it as a function of these angles, phi and psi. You can simply plot this thing, okay, in MATLAB and see how it looks like, because it looks very complicated here. But to understand in a simple way, again, you have this 2D sinc function, okay? Remember that 2D sinc function, the slices of it will look like 1D sincs, okay? And again, this will be a surface in the 2D case, 2D sinc surface. And just as in the 1D case, take like two minus infinity and plus infinity points ends, and just squeeze the 2D sinc function. You're gonna get a function like this. Maybe a better plotting, I can show you a better plotting of this from your book. It's here. Okay, yes, this one. This is for circular, circular uniform illumination function. So this is JINC now squeezed in the way that I explained, but it will look very similar to the sinc case or the rectangular case. In this one, it's shown in the other direction. Okay, so this is again the propagation direction. Z is here in this illumination, in this visualization. If we go back to our plot, okay, this is my propagation distance Z, and we see that this pattern, this 2D pattern for rectangular uniform illuminated antenna, it will look like this. Okay, and this is, I wanted to say one thing here. Okay, you see that this is pointing the propagation direction. Okay, so if you use a simple rectangular illumination function, then your antenna radiation pattern is pointing the z-axis. Okay, mostly. And there are like side lobes due to like zeros you have. Again, here you have 1 0 here, another 0, second 0 here, third 0 here. Okay, so those are all coming from the angles that makes inside of these expressions integers. Okay. Now, okay, this is for a single antenna element. We want to understand the antenna radiation pattern of the antenna array. Okay, what's going to change? We're going to modulate this pattern with this two-dimensional Dirichlet function. Okay, what was, how will that look like? If you think about the, if you consider a slice of this function, okay, this was the slice of the 2D sinc. Okay, on the fx axis, we're gonna basically modulating with this Dirichlet function, 1D Dirichlet function. Okay, this one. What was a Dirichlet function? Remember that Dirichlet function was a periodic function. Okay, and it was taking exactly the same values at its periods. Sometimes its signs alternates between plus and minus, depending on whether the n and m values here are even or odd. N and m are even or odd. But suppose there is no sign reversal, so it's only repeats itself. And remember, the first zero crossing was appearing at 1 over n. N is the number of periodic structures. And it was repeating itself with the integer 1. Here, of course, there is a scaling here. Okay, so your Dirichlet function is scaled with L over D1. Okay. So if you also consider that scaling, your Dirichlet function will look like terms like this. Okay, but you are modulating the sinc with this Dirichlet function. That means this Dirichlet function, after modulation, will hit this plot. Okay, at the maximum values, we're gonna just hit this plot, this slice of sinc function. Okay, so the result of modulation will give you in the 1D slice this little oscillations. Okay, again, if you think of like squeezing this thing, what you're going to observe here, it doesn't look great here, but let me make this plot better. You're going to see, for example, here, this type of smaller lobe, okay, which is due to this term now, okay, this portion. And then you're going to have, due to like these portions, you're going to have this other lobes, okay, for example, this one and this one. Okay, so you will have like smaller lobes inside this bigger lobes. Okay, that will be the effect of modulation with Dirichlet. And you're going to similarly have the same smaller lobes inside this bigger lobes. Okay, and that will be your pattern for the antenna area. We're gonna discuss later, but let me mention that the resolution achieved by the by a radar imaging system will be highly related to the size of these lobes, the first lobe, okay? How large the first lobe is. It will depend on that a lot. And that's gonna depend on how large your each single element here, how large your L here, and how large your repeated structures, N and capital N and capital M are. Okay, as you increase L, N and M, you're gonna have a smaller and smaller main lobe here, okay, which is gonna improve your resolution in the system. Okay, so the antenna designer's task is actually to decide on this illumination function, to decide on this L, the antenna size for each element, and how many to repeat. Okay, and based on that, you're gonna get the limitation for the resolution of the system. Okay, so that's for now all I want to say about this example. Here, let me mention one more thing. Here, I told you that this antenna pattern is pointing directly the Z direction, okay, with no angle with Z direction. So it's directly pointing to Z direction. But you can, again, design your illumination function as in a way that you point not this Z-axis direction, but with some angle maybe, okay? So you can steer your beam into a desired angle, spatial angle. That's known as beamforming as well. Okay, related to digital beamforming. It can be also analog as well. So you can change. So here in this example, we said that in this antenna array, all these elements are identical. Okay, they all have the same illumination function S0 XY. But if you change the phase of these, if you change the phase of each element in a particular way, in a designed way, then you can change where your beam is looking at, okay? Or you can change the pointing direction of your pattern. That's again a design task, but you can study that, okay? So if your each aperture element do not have the same amplitude and phase, if they have different amplitude and phase, you can steer your beam into a desired angle, okay? And I will give you a task for this in the homework, okay? So you will look at how to choose the phase, how to change the phase of each element, single element, so that your beam will not point this direction, like here, but the main lobe will point, for example, in an arbitrary angle, okay, an arbitrary direction. So you can do those things once you understand this relationship. Okay, once you know the relationship between the radiation pattern and your illumination function, then you can now state tasks like what should be my illumination function to achieve this pattern. Okay, and that's what an antenna designer will do mostly. Okay, you should first understand it mathematically, and then of course you should physically implement that. That should also be possible. Okay, So these are more like antenna design topics. Okay, now that was the antenna part. Now we're going to discuss another concept related to radar imaging, ambiguity function. Ambiguity function is a tool to understand how good like radar signals we can pick to measure both the range and the velocity of a target at the same time. Okay, so ambiguity function will be useful for us to measure the range of a target or distance of a target, distance of a moving target, and its velocity at the same time. And it will help us to understand the trade-off between these two measures. So in general, you can think that why do we use a radar system? Okay, the radar systems in general, they have two general purposes. The first one is to understand the range of a target that is in the that's far away. Okay, so we want to find the distance of that target. Okay? That's, for example, used in many defense systems. And that range of a target is generally understood through time delay information in the radar signal. Okay, we're going to discuss that. And another place where radar is very useful is to understand the velocity of a moving target, okay, towards a radar system. For example, that's used to measure the speed of cars, right, through radar systems. And this measurement relies on the principle of Doppler effect, okay, and we're going to discuss that as well. And ambiguity function will tell us what are the trade-offs between measuring these two things at the same time. Because in radar imaging systems, our goal is generally to measure both the distance of a target, the range of a target, and also its velocity at the same time. But there is a trade-off between these two. Okay, and that's going to be understood through the ambiguity function. Okay, before going to the discussions about ambiguity function, let's understand what is a range measurement in general for a radar signal, how a range is measured, and how the velocity is measured for a target. Let's first understand the range measurement. What we're going to have, okay, we have a radar system. Okay, there's an antenna here. Okay, it can be anything. So there is a radar signal transmitted from this antenna, okay, and that is transmitted. Suppose there's a target here, and this radar signal is transmitted, okay, to this target, and then it's reflected back from the target. Okay, so the transmitted radar signal first goes this way, and then it's reflected back from the target, and it's going to be received back from by our antenna. Okay? So here our antenna is both a receiver antenna and a transmitter antenna. So we first transmit by the same antenna and receive by the same antenna. Suppose the range or the distance of the target to the radar system, the antenna system, is d. Okay, and our goal is to determine this d, the distance of the target. How we're going to do that? To do that, we need to first understand our received signal. So if we call the transmitted radar signal from the antenna as S of t, okay, suppose S of t looks like this, then the received radar signal will only change by the transmitted radar signal approximately by only a delay. There can be also like the amplitude changes as well, but that's not very critical, we ignore that. So the critical part of the received radar signal will be, it's going to be the delayed version of the transmitted radar signal, because it's going to travel this direction, this path of 2D length, okay? And then we're going to get the delayed version of this S of t. Let's call the delay tau. What is delayed tau in relation to my distance d? Okay, so my signal, radar signal, travels a distance of d and then another d to go back. So it travels a distance of 2d. Of course, it's going to travel with speed of light, c. So if we divide 2d with c, that's going to be the delay we will have for the received signal. Okay, so tau will be 2d over c. The delay is something we can measure in our radar system. We can observe how much delay we're gonna get the signal, transmit the signal back. Okay, so this is available to us. So if we solve for the unknown distance or unknown range d here, it's going to be tau times c over 2. Okay, so once we measure the delay, if we can measure the delay of the received signal in a reliable way, then that means we can also get the range information. So it's just the delay times c divided by 2. Here, the question is, once we understand this, let's think about what is the best radar signal, S of t, to use to measure this d in a reliable way, to understand the delay in a reliable way. Okay, so if, of course, the best signal here will be if S of t will be the impulse signal for S of t. If S of t is an impulse signal, so it has a peak at some point, then in the delayed signal, we only need to look at the position of that peak. Okay, and just comparing the location, we can get the delay information. Okay, so the impulse signal or very peaky waveforms are best waveforms for measuring the range information. Okay, because if there is noise, there will be always noise on top of our measurement, radar measurement, due to clutter coming from the environment, many other effects, okay, many other unwanted signal received from the environment. There will be noise, but if we have an impulse or very peaky signal as the radar signal, we will still differentiate or identify the peak point, and we will be able to identify the delay amount easily. Okay, but remember that impulse, if you look at the Fourier transform of an impulse, what you have is constant in the frequency domain. So you'll have uniform distribution in the Fourier domain. So impulse is a wideband signal in the frequency domain. Okay. So you basically, if you want to have a very peaky signal as your transmitted signal, you need to use wideband signals that has large frequency portion. Okay. In the frequency domain. So that seems like the best signal to use for the radar range measurement. Okay, let's continue. That's for measuring range. Let's understand also how we measure velocity of a target using a radar signal. Again, we have an antenna that transmits a radar signal, S of t. It hits a target. Our target is now moving. Let's call its velocity v. Okay, it's moving toward the antenna, toward the radar system. And again, we're gonna have a signal transmitted and then reflected from the target, and we're gonna get R of t. Okay, so again, there will be a delay, of course, due to this traveling distance, but let's ignore the delay for now to understand what will be the effect of velocity of this target on the received signal. I'm ignoring the delay for now. Let's understand what will be the change on the received signal other than the delay. Okay. To be able to understand that, we will restrict ourselves to narrow band signal, S of t. Suppose S of t is a narrow band signal, so it has a narrow band in the frequency domain. And suppose it is centered around f0. So mostly S of t is a signal that contains frequency f0 and maybe some frequencies around f0. Now, what will be the frequencies in the received signal R of t, if that's the case? Okay, so the frequency, we know that the frequency of R of t will be different than S of t due to the Doppler shift effect. Okay, what is the Doppler shift effect? If we have a moving target, if a target is moving towards us, and if we are transmitting a signal here, okay, so we're gonna sense the frequencies higher than it is. okay, if it's moving to us. If it's moving far away from us, we're going to sense the frequencies as lower than it is. Okay? So the frequency will going to change. Okay, so in the case that V is positive, we're going to have a frequency increase by the amount of Doppler shift. And what is that? That's basically V over lambda wavelength. Okay, and if you write the wavelength in terms of a C and frequency of the signal, it's just V divided by C times F0. Okay, that's the increase in the frequency due to the speed of the target. Okay, so the observed frequency in R of t will be F0 plus V over C times F0. Okay, or if you write in F0 parentheses, it's going to 1 plus V over C. Here, delta V is representing the speed difference between this point, the object here, which is our antenna, which is stationary, it's not moving, and the target. So delta V here is actually V as well. Okay, V, this the difference, the speed difference between these two, because this is not moving, is V. Okay, so the observed frequency, the frequency of R of t signal will become this thing. Okay, the original signal was centered at F0. This is going to be centered at F0 times a factor. Okay, this is telling us that in the frequency domain, R of the signal will be enlarged. Okay, so our frequency, okay, before we had a peak around F0 in the frequency domain, but now our peak is in a higher frequency. Okay, that means you stretch your signal, S of t signal, in the frequency domain by this factor. Okay, that's kind of what you're going to observe for R of t in the frequency domain. Okay, so because you can interpret this as frequency scaling by amount of 1 plus V over C, the effect in the time domain will be scaling by the same, by the reverse amount, 1 over 1 plus V over C. Okay, so that means you can roughly, this is of course an approximation, you can roughly express your R of t signal, the received signal, as the scaled version of S of t signal, and the scaling amount here will be this. So you're scaling it, you're squeezing it by this amount, okay? You're enlarging by this amount in the frequency domain, you're squeezing it by this amount in the time domain. That means your A should be this value, okay? But here you have a square. We also should have a square. Why that's the case? Because our signal transmits, travels twice, okay? So it first goes this direction, okay? That's gonna the Doppler, the amount of Doppler shift you're gonna see if your signal travels from here to here, okay? But then it travels back, okay? It's gonna experience same amount of Doppler shift in that case too. So you're gonna see the scaling twice, okay? So that's why we have square here. If you want, you can approximate this term because V over C will be generally very small, okay? You can use the Taylor series expansion to approximate this term as 1 plus 2 times of this term, 2 times V over C. Okay, so you can simply say that your scaling here in your R of t will be by this amount. Okay, and as it should be, it depends on the velocity information. So if you can measure how much your transmitted signal is squeezed or enlarged, okay, from that information, if you get that scaling information, you can understand the velocity. If you can measure A, the scaling amount, you can also get the velocity of your target, okay, using this equation. Again, if you think about what should be the S of t signal, the received signal, to pick to achieve this in the best way, the best signal to achieve this will be an impulse in the frequency domain, because you want to understand how much you enlarged a signal, okay, in the frequency domain. If you have a peak in the frequency domain, then you will easily identify where that peak moved in the frequency domain. And by looking at how much enlargement you had in the frequency domain, you can get the scaling information in the time domain as well, and you can get this velocity information in a reliable way. Okay, because of this, you basically want an impulse or a very peaky signal in the frequency domain. That means you want a sinusoidal signal or a very narrow band signal to use as S of t to measure the velocity in the best way. Okay. But here you should notice one thing. Remember that impulse was the best signal to measure the range, and sinusoid is the best signal to measure the velocity, but in some sense they are opposite of each other. Okay, one of them is impulse in the space domain, the other is impulse in the frequency domain. So you cannot design your S of t in this in a way that you measure both the range and velocity in the best way. Okay, there is going to be trade-off between measuring range and velocity for choosing your radar signal. Okay, that's unavoidable, that trade. And how we can understand that trade-off is going to be through the ambiguity function, and we're going to discuss that in the next lecture, which is going to be in the next